Hi, this is Jeff Evans from Evans Performance Academy. We're going to be taking a look at some basics with our PC Link software so you can get started with your Link G5 or G4X system. Without further wait, let's jump in to check this out. Okay, so let's get started. We're going to be taking a look at working with temperature sensor inputs and programming for our Link G5 and G4X systems. In this tutorial, we're going to be specifically taking a look at setting up engine coolant temperature and intake air temperature. These are the two basic temperature sensor inputs we'll have for any installation on any engine. We may also find you're wiring in engine oil temperature, or even something like transmission or differential temperature. You can use other temperature sensor configuration and input setup with the Link. What we'll learn from setting up our engine coolant temp or intake air temp will apply to setting up any type of temperature sensor input in the programming. Very straightforward, so we're going to dig in here and learn how to do this. So first things first, because my G5 is a fresh installation here on my Honda K-Series engine, I have not assigned any temperature sensor inputs to the Link. This is the default file, the G5 file that they provide. As a result, we're going to see that the engine coolant temperature and inlet air temperature are both reading 32 degrees. This is a default value in its reading. We need to go in and tell the Link where we've wired in terms of the input for the sensor, and then what type of sensor we're working with, and essentially giving it the calibration scale. It's very easy to do this, but there are some specific things we need to note and pay attention to. Let's jump in and take a look at where we can program both of these temperature sensor inputs. We're going to move from our basics page right here, and we're going to go across to our analog input page. Here we can find engine coolant temperature, ECT, and intake air temperature, IAT. This is where we do the actual programming in these windows. We also find engine oil temperature as the other common temperature input easily programmed within this window. If we have something in terms of a temperature sensor input that's not found within the predefined ECT, IAT, or engine oil temperature, so for example, transmission temperature, we can use a general purpose input, which we can find right here, GP temperature 1. We can set up a custom name and then tell it where we've wired it to, and then set up a calibration scale so it understands where to find the sensor and how to translate a voltage or resistance value into an actual accurate temperature sensor reading. Okay, let's first set up engine coolant temp and intake air temp here within our window. First things first, engine coolant temperature. I'm going to set this up because this is the very first one on the list. Now I know where I've wired my engine coolant temp and intake air temperature in terms of the inputs to my G5 box. I've actually wired engine coolant temperature into my analog temperature 2 input and my intake air temperature to the analog temperature 1 input. So I know where those pin designations are for both temp sensors. If you're unsure of which is wired, so where either is wired, setting up a fresh install, maybe you didn't get a pinout chart for whatever reason with the vehicle, with the harness, and you're trying to sort things out, you can use your runtime values list to actually find this and sort this out very quickly. If you go to tuning and go to runtime values, we can see here on the analog screen, we have our analog input states. Then we find we have analog temperature and analog temperature status. Here we can see what the actual raw voltage is reading on the Link for these particular channels. Now, I know analog temp 1 and analog temp 2 are what I have wired in for engine coolant temp and intake air temp. Analog temp 3 and 4, note that they're reading 4.95. This is open circuit, so they haven't been assigned and nothing has been wired into them, so they're going to read a high voltage value. This is going to tell you that these aren't being used, but we find that there's voltages a little bit lower than that here. It's going to tell me that both of these are in use. So it confirms my wiring that I know. I've already written down the pinouts and I know which ones I'm using, but this confirms which is which. Now, if I didn't know which temperature sensor was which, I could unplug the temp sensor, and if you see it change to 4.95, then you would know that is going to be that particular temperature input associated to the sensor. So if you're trying to sort this out, then once it's assigned, you can see the status here showing that it is activated or not. Right now they're showing off because we haven't configured anything in our windows right here. So as we're noting, we have our analog inputs, map, and fuel pressure. Note that they're both showing here active status and that they're assigned to these particular channels. It'll show this once we're done setting up and calibrating our air temp and engine coolant temp, it'll show that status down here in this window. So the runtime value window can be a valuable window to take a look at if you're unsure of which sensor is wired to which input. You figure that out pretty quickly, so I wanted to mention that. All right, let's close this up. Okay, now let's jump in and take a look at how to set up engine coolant temperature. Again, looking at this, it's reading a default of 32 degrees Fahrenheit, simply because we haven't defined the input and defined the calibration scale for the sensor we're working with. If we jump up here to source, we double click, this is going to be where we tell the link where the sensor is wired to. In this case, I'm using my analog temperature input. So I have analog temp 1, 2, 3, and 4 as my option. We can wire a temperature sensor into an analog voltage input and not an analog temperature input. However, if we do this, you have to wire an external pull-up resistor. This is definitely kind of a pain to do. I would recommend anytime you're doing any wiring, custom wiring with your link, wire it into an analog temp if it's a temp sensor. Otherwise, if it's a pressure sensor, then you can just use an analog voltage input. Okay, engine coolant temperature in my case is going to analog temp 2. I click OK. Now we have some information that populates. The first thing we're going to notice here is that our analog temp 2 pull-up resistor is set to the internal 1K ohm pull-up resistor. This is an important detail we'll talk about here when we set up our intake air temperature. Right now, we don't necessarily need to worry about this or care much about it, but this is a detail that does matter if you're setting up a custom calibration scale for your sensor. Now, looking here, we have an air low and an air high. I will leave these at these default values. Typical temperature sensors will have a range of 0 to 5 volts. This is going to be the two extremes here, 0.05 and 4.95. It's saying if the sensor becomes unplugged or there's some kind of a short in the sensor or short in the circuit, it'll go below or above this voltage. It'll flag that as a potential problem in the circuit, and it'll tell us when we open up the software up here, it'll display actual codes and show you that you have a fault on that circuit. So this is going to be our thresholds that we have to trip for it to turn on to the fault, and then when it does fault, what the error value goes to. I wouldn't recommend to do 32 degrees Fahrenheit. I would recommend to set it at something like 160 degrees Fahrenheit. Now, if you're used to working in Celsius, if you use the U button, in this case, U is just switching the PSI and KPA. I wasn't sure if it was switching Fahrenheit to Celsius. You can change this from Fahrenheit to Celsius under options, under preferences. You can switch this under the units to whatever you'd like it to be. So just keep that in mind if you don't want to set things up in Fahrenheit, you want to do in Celsius. Okay, so if it trips and faults out on that sensor, it'll go to 160 degrees Fahrenheit. Now again, the reason why I didn't stick to 32 degrees is because at 32 degrees, you're going to have things like your engine warm-up enrichment being applied. It could make it run extremely rich and bog down and create some problems of over-fueling on the engine. Likewise, it could advance the spark timing if you have a engine coolant temp ignition advance setup so that it helps it stabilize on a cold engine. That could apply itself, and if you're under full throttle, that's definitely not desirable. 160 will make sure that there's no warm-up enrichment applied, and we're not adding additional spark timing advance, which could damage the engine. So I'll leave it at 160. The last detail we need to take care of here is the calibration scale. Now, we double click here, and it brings up our list. None means that there's nothing calibrated. Here we find a lot of options in our drop-down menu that we can choose from. Again, taking a look here, we have a lot of options. Now, towards the bottom here, we have calibration tables, which is what we actually have to use to define a sensor that's not in our drop-down list or menu here. Now, it just so happens because I am on a Honda K20 engine, I'll be choosing Honda K20 here and click OK. Now we can see the engine coolant temperature, key on engine off, is sitting here about 57 degrees Fahrenheit. Now, if everything's correct, this should match on a cold engine ambient temperature. This seems a little bit off to me right now. However, I haven't measured the actual temperature in the engine bay and in the room, so this could be fairly close. I was thinking it was more about mid-60s, but again, I haven't looked at the actual temperature yet. So, we find engine coolant temperature should match ambient temperature approximately. Intake air temp is going to be the next thing that we need to take a look at. this is where we're gonna have to do a little bit of custom programming. So I'm gonna show you some details now that can be applied to setting up a custom sensor, such as general purpose temperature input for transmission temperature. You may have to go in and do this because likely the temp sensor you're using isn't going to be in that drop-down menu that we just chose here for the calibration. All right, let's go to source. Now in this case, I know my intake air temp sensor is wired to analog temperature 1. I'm going to go ahead and assign that. So we'll double click here. We're going to go down and we find analog temp 1 is what we want to choose, and we'll click OK. Now we have our air low and high values. This is going to depend on the sensor and the scaling of the sensor. Generally speaking, again, temp sensors are 0 to 5 volt scaling, and generally speaking, having it set to the extremes here is acceptable for the low or high air. Again, air temperature, air value, I would set this to maybe something like 70 degrees Fahrenheit. This is kind of an average temperature. If it faults out and the air temp is super low in terms of the error value, that's what the channel will actually read. That could be problematic for us. We want to avoid that so that you don't have any kind of odd fueling compensations in play if the sensor faults out. Now obviously you don't want to race it like that, but we want to make sure that it's not doing anything kind of odd with our calculations in fuel or spark timing. So we've set up here the temperature input in terms of the source, the min and max values. We know that that pull-up resistor is 1 k ohm. That's going to be important in this case. The calibration here, we need to go to the next step. I am using an AEM temperature sensor. It's not found on our list. I actually have the data sheet pulled up here from AEM. This is going to be a 30-2014 air temp sensor, which we can find right here on the right. So what they provide us here in the actual PDF sheet, and this is the data sheet you'll find for other types of sensors. So the format here will be similar. It's not going to be the same, but the format will be similar. Let's say you're using a Rife sensor, or let's say you're using some type of a Bosch sensor. You should be able to obtain the data for the sensor. What we're looking for here is being able to see what the sensor resistance in ohms is going to be, and then what the associated temperature is going to be. So we need to program this information into the link so that when there's a certain resistance or voltage reading coming in, it can translate that to the proper temperature value so the temperature sensor is reading correctly, and anything that's looking at in terms of a compensation, air temperature, it'll be correctly indexing the temperature, and we won't have any problems with fuel or spark timing. So very important that we set this up right. Okay, so here's where the details come into play in terms of that pull-up resistor. We can find here, we know if we go back in the software here, the pull-up resistor is going to be a 1 k ohm. Now, here's where we need to pay attention to some things. When we're setting up the calibration scale for the link, so let's just close this window out for a second. When we're setting up the calibration scale for the link, and if we go back into the data sheet, we're working with a 1 k pull-up. What we'll find here is that AEM is giving us the sensor resistance in ohms, so this is with no pull-up resistor at all, and then they're going to tell us what the translation is going to be with a pull-up resistor in voltage. Now we have the option with the link to enter in ohms or voltage. This is where we need to pay, again, attention to the details. We're not dealing with a 2.2 ohm, 2200 ohm or 2.2 k ohm, or a 2.49 k ohm. We're dealing with a 1 k ohm. Now, how do we deal with the sensor data and translating this? Because this is tricky. Let's first go in here and take a look at setting up the link, and then we'll jump back in here and talk about this. Go back into the link. Let's go here into the calibration scale. What we'll be using here is a calibration table. Let's jump down to the bottom of the list because our AEM sensor isn't found in this list. We go down here, we're going to find that we have these cal tables 1 through 10 available. Then we also have linear cal tables. Now, the last training module we talked about setting up a linear cal table for a Omni 4-bar map pressure sensor. When we're talking about a temperature sensor, they're not a linear calibrated style sensor like a pressure sensor. They're going to be unlinear in their calibration. So we need to use a calibration table for a temperature input if we're doing a custom setup. I'll go here to cal table 1 and click OK. Now the link is going to be taking a look at our cal table 1 information and translating the resistance or voltage into a temperature sensor reading. Now, first thing we're going to notice here, the air temp is showing 212 degrees Fahrenheit. This is obviously incorrect because our calibration scaling in here is not correct. Let's go into the cal table one, and I'll type in here AM IAT, so I know it's the AM sensor. The input type, I'm going to stick with units of volts. Now again, we can go in here and use ohms, resistance, or voltage. There's a specific reason why I'm using volts, and again, this will make sense here in just a second, and that's going to be related to this 1K ohm internal pull-up resistor. Now the output units are going to be in units of temperature, so let's go ahead and grab temperature, click OK, and the cal table here, right here, if we double click, that's actually going to bring up the table right here. Now, this table is going to be associated to degrees Fahrenheit and voltage. We're going to be setting the top scale of the table to volts and the bottom scale of the table, that'll either be in units of Fahrenheit or units of Celsius. So we have to pay attention to the units we're working with here. Let's take a look at our data sheet here once again. This sensor resistance ohms is what we need to put into a course calculator. We're going to look at that. I have that open right here. We're going to enter this information in at these temperatures, so -4 all the way up to 302. That's our temp scale. And we need to account for that 1K pull-up resistor. We can translate that into a proper voltage for the lookup table. So this might be a little bit confusing. Let's just show you how this is all going to work so you can make sense of this. Let's jump into our Excel spreadsheet. Now this is our course spreadsheet, course calculator, found in our training course folder. You should have downloaded that already, and this will be present, and again, in this specific tab called Temp Calculator. Now in here, what we're going to find on the very right-hand side, this is going to be a calculator allowing us to translate the resistance into an output voltage. And the voltage here, looking at this particular channel, this is typically 5 volts for a temperature sensor circuit. Most standalones will all be 5 volts, so we're going to leave this value alone. The pull-up is going to be here in terms of ohms. Our link is going to be a 1K ohm internal pull-up. 1K ohm is 1,000 ohm. So in the spreadsheet here, I'm going to have a value here of 1,000. Now, if we take a look at this real quick, the resistance, this value right here, assuming a 5 volt reference and a 1K pull-up, translates to a output voltage of what we find right here calculated at 4.82. What we want to do here real quick, take a look at this, jump in. If we take the first point of our data sheet here, 28,136 ohms translates to -20 Celsius or -4 degrees Fahrenheit. We want to enter this value in here so we can just see this conversion real quick. What this is going to do in the calculator is take this ohm value and translate it into a voltage value that we can enter into our voltage table. So let's look at this real quick. So it looks at the value here, I've already entered it in. 28,136 ohms, 5 volt reference, 1K pull-up, translates to a 4.82 volt threshold. So what this is going to tell me and what I need to do with the link is create a breakpoint in the table right here so that we have the voltage value of, from our data sheet here, 4.82, and then we associate that to whatever the temperature is from the data sheet. So that is going to be -4 or -20 Celsius, again, depending on the units. Now, the link right here is set, jump back into the link. The link is set to units of Fahrenheit. We can actually update that. Let's just change it real quick. Let's go here to units. Let's do imperial. Let's flip back in here to metric. I have, depending on, let's go in here real quick. If we have the options, we can see here on the metric units, I've set the temperature that I want. If I'm set on metric, I want that set to Fahrenheit. I can switch that to Celsius, and now we can see it's showing 100 degrees Celsius. So let's switch it around. The reason why I'm going to work in Celsius is because it's a little bit easier, I find, when we're setting up a programming data. You can always switch it back to Fahrenheit by switching your units, but it just keeps things a little bit simple. Let me demonstrate. We can find here in our list Celsius on the left, resistance here in the middle, and we're going to translate that to a voltage. Now, what I've created here in the calculator, we have our Celsius that we can enter here from the data sheet. We have our resistance that we're going to enter in from our data sheet. It's going to automatically calculate the voltage here in the middle column. This is assuming that 1K pull-up and a 5-volt reference. That's what we have working with the link. Then it takes us a step further where it plots on the upper axis here what the voltage is at what temperature. And again, this is working in units of Celsius. So it's taking what we find right here and putting it into this format. This is associated to that linear cal table here in the software. So if we jump back in here, that's what this table ultimately is going to end up looking like, what we find here in the data sheet. So I tried to kind of mimic that. Let me go in here and start to enter in the first few entries so you get an idea of how to do this, and then I'll enter all the information in and I'll come back in and we'll kind of speed through the video because you don't need to watch me entering in all the data. You can do it right from your data sheet. So the first point of reference here, if we're taking a look at this, let's go in and type in the Celsius. Let's go to the data sheet and we're going to work with negative 20 degrees Celsius. That's our very first point. Now, noting and looking at the data sheet here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 total data points they give us in the chart right here. Link can only take 16 total data points in a calibration table. So we have to be mindful of that. I'm going to make sure I'm accounting for that when I'm setting this up. So I'm going to start off here at negative 20, and I may have to skip some data points, 2 data points in the table here, just to make sure that we get a whole curve for the actual reading. So if we take negative 20, type that in here, right here. So on the left, we type in negative 20, and then the resistance, we type it in here. That's going to be that 28136. It comes right from the data sheet. Again, looking across, so negative 20, 28,136 ohms, and we calculate the voltage here in the spreadsheet here of 4.82, 4.83. Now, when this happens, when we have it right here, notice it automatically translates right here in the actual table. So that's what we're going to be translating then into the link. We'll look at this here in just a second. Let me do the next data point so we have that entry. We'll type in negative 10 Celsius. We have to type in the proper resistance that comes from the data sheet again, 15,813. So let's type that in here. So 15,813, enter. And now we have a new voltage that we need to go and enter into our chart table. And we can see that changes it right here, so that lookup changes. I'm going to manually enter in the rest of the data here into the calculator and allow this to populate. And then we'll come back in here and we'll take a look at the next step of translating what we have here from the spreadsheet to the the cal table, and then we'll see how that all translates and see what that looks like. All right, I'll be back here in a second and I'll go through all this and we'll continue on. Okay, so I just got done hand fitting all of the data from our data sheet into our chart right here. So what we're gonna find, what we're left with here, is we have a voltage scale to enter into our calibration table, and then a temperature scale associated to that new voltage scale. So we've translated the data from the sheet to our 1K pull-up ohm on our actual internal circuit, so we're accounting for that. We've entered in the resistance, the temperature, accounting for the pull-up resistance. Now we have a corrected voltage to temperature scaling that we can enter in. So this calculator helps a lot. Let me go and demonstrate the next step here. So if we jump into the software, we find this linear cal table. We're going to click right here on the linear, or not the linear cal table, keep saying linear cal, the cal table, and we're going to click X. This allows us, again, working in units of voltage, to enter in our voltage scale. Now, unfortunately, looking at this, I'd love to be able to copy right here on our scale. So going in here and actually highlighting and doing Control-C, copying that, jumping into the link software, and going in and pasting all of this across. So we see we have 16 data points, paste, Control-V. Doesn't work that way. I have to manually enter this in, which is definitely not ideal, but let's go ahead and do that. And I'm gonna go ahead and just start to do this and speed this up. I'll come right back into the video once I have it all entered in, but first data point here from our spreadsheet is going to be 0.206. Let's go ahead and enter that in. So it's going to be 0.206, enter. The next, and see it rounds it up to 0.21, so there's going to be some round up there. Let's go and enter the next data point, which would be 0.27.
and I'm just going to round these numbers up, make them a little bit simpler. So I'm going to edit the entire table here based on what I have calculated in the axes. I'll come back in a minute here after I'm finished, and we'll move on to the next step. Okay, so I've entered in the last data point. If I click OK, and then I'll say yes, we'll just allow it to interpolate. Now we see the table has been created here. Let's go ahead and just stretch this table out so we can see the full scale of this table. Let's go stretch it out here just a little bit more. I might have to move the position here to stretch it to the full scale of the table. So we'll see here, now the table has been populated. Let's slide this back into place in our window here. So now we have that corrected voltage scale, as I was mentioning before. And now what we're left with here at the bottom is actually defining the voltage to Celsius, so the voltage to temperature translation. Now, in here, I'm going to try this. I don't think it's going to work. If I copy this, I don't think it's going to paste. Let's see if it's going to allow us to do this, make it easy on us. So highlight here, Control C. Let's jump back in here. And let's do Control V. And it does. It works. Copy and paste. Now, what we're finding is, looking at this, we're in units of Celsius. Air temp showing 21 Celsius, engine coolant temp showing 14 Celsius. They're differentiating from each other here a bit. That isn't unnormal, but there is a decent spread or deviation here. So what I'd probably want to do is this engine coolant temp scale may not be correct for the Honda K20. It may not be correct. I might have to dig that up what the actual calibration scale is going to be because it's not seeming like matching the sensor. So key on engine off, we should find that these are fairly close to each other. Let me switch back over here just to Fahrenheit units because that's what I typically work with. And we can see, yeah, there's about a 13-degree spread between these. So I'm going to trust that this the calibration table we just created for the AEM air temp sensor is accurate. However, the engine coolant temperature something here I need to double check because that is going to be the link scaling. Now what we can do from here to save ourselves some time because it took a bit of time to create this calibration scale, we can actually right click and go to export. So say export to file, and let's go in here to our desktop. I'm going to put this into the G5 course packet. We can find in the calibrations folder under the sensor data. You can go in and then export this out. So I can call this AEM, and the part number for the sensor here is 30-2014. So we can enter that in here. So we'll say enter 30-2014, enter. So we have this calibration curve saved. So if I use this sensor again, I can just select my setup here in a cal table and do an import and import this calibration data in, saving me a ton of time. As you can see, it took a little bit of time to populate and do all of this legwork. But now I know my sensor data is accurate and I can trust it. Again, we can't just take the data from our sheet here without accounting for the internal pull-up resistor, which is why I've created that spreadsheet in order to enter all of the information in and do it correctly. Okay, let's jump back in here. That is going to be it for setting up temperature sensors. Again, I'll have to double check this engine coolant temp because it should be matching within maybe 2-3 degrees of our air temp sensor. And in the garage, I was thinking it's about mid-60s. It's probably closer to 70 to realistically. So it's going to point to my engine coolant temp sensor not being, in my opinion here, calibrated correctly. So there could be something wrong with this calibration scale. However, that is going to be how we set up our temp sensor inputs. So we have the ability to use a drop-down option, or we have the ability to use a cal table to build out a custom cal table. If your oil temp sensor isn't fitting in the drop-down, you'll probably build a cal table out for the sensor. Same's going to go for a general purpose sensor, general purpose temp. If you're going to be using that for differential or transmission temperature, you'll find that you probably have to do the same thing with another cal table. So that's going to wrap it up here, taking a look at setting up and working with our temp sensor inputs.
Thanks for watching our tutorial. If you're interested in learning more about how to tune your Link G5 or G4X system, check out the video description below where you can find links to our school, some promo codes to get you started and save some money. If you're interested in learning more about Link engine management products, also check out the video description below. That's going to wrap it up here. I hope to see you guys in our school.